Alright, so in this video we're going to describe an application of linear functions. Now, linear functions are extremely ubiquitous and there isn't any way that anyone could describe all of the possible applications. The thing to do is to be able to recognize what situations in real life are linear, and then the underlying mathematics then will always be the same. So, let's take a look at this scenario here. So Dr. Johnson is traveling to her mother's house at a constant speed of 75 miles per hour. Then after 3 hours, she passes a landmark that she knows is 200 miles away from her mom's house. And what we want to find is a function that describes her distance to the house in miles after t hours of travel. And then we want to know how far away she started off initially and how long did the trip take overall. Now, what tells us, of course, that this scenario is modeled by a linear function is the fact that her speed is constant. It isn't going up or down at different points. And so we can go ahead and approach this problem as we've done the purely symbolic linear functions that we've dealt with before. Now, let's take a good look at A and let's see what information we have. What we have is a constant 75 miles per hour, right? Now, if the function we're trying to describe d of t is the distance from her mom's house, what we know is that every hour that distance decreases by 75 miles. So what we have is a slope of minus 75. And then what we know also is that when t is 3 hours, right? After 3 hours of travel, the distance is 200 miles. So summarizing down here, we have a slope of minus 75 miles per hour. And we know that when t is 3, the distance is 200. That's a slope and a point, and that's exactly enough information to identify a linear function. And again, you can use different ways to do this. I'm just going to go ahead and use the point slope. So we know is that d is equal to minus 75 t minus 3 plus 200. So that means d is minus 75 t plus minus 75 distributed with negative 3 is 225 plus 200 which gives me minus 75t plus 425. So that's my distance as a function of time, right? And so we can go ahead and plot this out, and that might help us answer the other parts as well. So what we have is d of t is minus 75t plus 425. And what we have here is a very awkward graph whose x value is sort of miscale. Let's rescale it like this. So that's our d of t, right? And so we can see that she starts here, right, when t is at time 0. So she's 425 miles away, and she gets closer and closer and closer until the distance from the house is 0, and she's at her mom's house. And so, graphically or geometrically, we can find the solutions to these problems. And let's just go ahead and confirm them algebraically. So part B was, how far away did she start? We've already seen the solution, but let's go ahead and work it out algebraically. When she starts, time is 0. So she's at time 0. So we just take our d function, evaluate at time 0. This, of course, is all 0, and we're just left with 425 miles. So when she sets off, she was 425 miles away, which is consistent with what we saw here, right? The second question is, how long did the trip take? So we want to know what time it was when the distance was 0. So in that case, we have that 0 is minus 75 plus 425. Sorry, minus 75t plus 425. So we have that 75t is equal to 425, or that t is equal to 425 over 75. Now, there's quite a bit of cancellation that one could do here. You could, for example, divide the top and bottom by 25. That'll leave you a 3 in the denominator. On the top, that'll leave 1, 16, 17. In the numerator. But there's no reason to go through all of that if you don't feel like working out all that arithmetic. What we're looking at is 425 over 75. And that, we can think of it as 5.6 repeating, or 17 thirds, which is what we just confirmed here, right? So, in about 5 2/3 hours then, right? Just under 6 hours, 5 hours and 40 minutes, in fact, is exactly the amount of time it would have taken to make this trip. So, hopefully that was instructive. If you have any questions, or if you want to see other examples, as usual, please let me know. Again, thanks for watching.